מזל שזכרתי. Keep talking. Everything is recorded right now. And the microphone is super sensitive. Everybody can hear you. Try to whisper.
If you think loudly, we'll record it too.
Guys, in Zoom, it's a pity I can't show you who is here. All the who's and who's are coming physically. Yeshua, Ezra, the dean. Once the dean is seated, we can start. רואים אותי בסדר? לא בסדר. נצמיד ללוח. Okay, I think it's good time to start. Guys from home, Amir, can you hear us?
Yep, all is well.
Very good, and it's also recording, so welcome everybody. A very unusual seminar, Omicron style. We have many people from home, I don't know, can you count? Maybe over 20 for now. And we have like dozen people physically from 217. It's a seminar, dual seminar actually. It's in the TRS, the robotic seminars of autonomous systems program, and also a seminar of mechanical engineering faculty here at the Technion. The speaker, Professor Shai Revzen, also in dual hat, also a visiting associate professor at the Faculty of Mechanical Engineering. He's also giving a class here, collaborating with me, so it's a visitor of the faculty and also a visitor of TASP, which is kind of the host of our collaboration via the Kahan Foundation grant. The title is Learning Locomotion the Easy Way. Shai is from the University of Michigan, Ann Arbor. Anything else? And from Israel, from Haifa, from the Technion? No, I don't know. Hebrew University, but family ties to Technion. Family ties to Technion, right?
Mm-hmm. Yeah.
Okay, so it's time to start. And about questions. You can write in the chat. I'm sitting with the laptop with the chat. We're having three laptops operating this Zoom talk today. And you can write in the chat. You can raise your hand virtually, or I think you should give some stopping points where people can just open their mute and shout.
I will talk about that in a second.
Okay. Everybody can hear you whenever you unmute.
Okay, thank you all. It's a great pleasure to come and talk here in the Technion. And as Yizal mentioned, we have a collaboration through the Khan Foundation, so it's pretty exciting to be in the Khan building doing a collaboration funded by the Khan Foundation. I'm going to start with credits, because if I don't do that, I might not get to credit everyone who needs to be credited at the end. But there will be these slides, these sort of yellow colored slides in the middle of the talk between sections, and that's a good time to ask questions if you have questions. Otherwise, it might be a bit tight. So the main people who did this work are Professor Ross Hatton and my former student, Brian Bittner, who did most of the work with me. But everyone else on this slide have also done work with me. The lower row here are all grad students of mine. And I should mention that the BIRDS lab that I run in the University of Michigan does all sorts of stuff related to biological locomotion. We build a lot of robots, and we also do a lot of math. And I'm not going to touch on all the things we do. I'm going to touch on only these tiny pieces of what we do in the lab in this talk. So this talk is about learning locomotion better. And this is based on some ideas for model reduction in physics and dynamical systems, which Ross and I applied together and got some interesting results. But perhaps the starting context should be that when people try and understand locomotion, they look at a hierarchy of models. We can go with very abstract, or sometimes called template models, all the way to detailed simulations of animals. This is an actual animal that was thinly sliced and digitized and modeled years ago in my PhD advisor's lab. All of these are papers that have been written on these approaches, but I also really recommend the book that I also use for the class I teach here in Technion, by Inspired Locomotion, that came out just a few years ago. And these ideas that I'll be talking about today appear primarily in 2 chapters in that paper as well. So I'm talking about 2 core ideas of dimensionality reduction. One of them is called phase reduction. And people are usually familiar with phase reduction in the context that you see in the top row there, where we talk about oscillators. But really what phase reduction is reducing the dynamic of the system. There are a bunch of technical math conditions, but the template, the low-dimensional condition, is low-dimensional model is a subset of the anchor, of the higher dimensional model, that meets some mathematical conditions that basically imply, as a consequence, that the template state is a phase, which means it governs what happens in the long term with the dynamics of the anchor after all the transients decay. So this is a really important and powerful idea. It has many forms in dynamical systems theory, but phase reduction and primarily reduction to oscillator phase, to the simplest kind of phase that you're familiar with, is an approach I've been looking at for a long time. In fact, this is a video from my PhD where I tried to reduce a cockroach and show that a running cockroach tracking all the limbs moving through space is actually an oscillator. And indeed, when you project it on the first 2 principal components of its shape, what you see up here in the middle, it ends up being just a simple cycle in that 2-dimensional space. And in fact, you can do a density plot, and you can see that this whole running cockroach data set lives within this donut shape in some higher dimensional space. So it's basically a cycle plus noise. And this idea of a lot of motion that we see in nature is just a cycle plus noise. This stabilization of the cyclic behavior plus noise is one of the 2 key reduction approaches we use. This is the phase reduction. The other reduction is a really important reduction from physics. It's what's called symmetry reduction. And that is the observation that the laws of physics are reference frame invariant. It means that we can actually partition our equations of motion into 2 parts. One part is the frame in which whatever is occurring, and the other is the shape, that thing which remains unchanged or can remain unchanged as the frame moves. Now, this allows us in symmetry reduction to write the state evolution as a frame velocity in terms of shape. So this is how will my body move relative to a body frame of reference based on how my body changes shape. And the other part is shape velocity in terms of shape. So my body interacts with itself, and I need to understand its internal dynamics. So what it does is it really reduces the equations of motion by the dimension of the symmetry we have on hand. Okay, it simplifies the equations. And this was done back in the 1990s by Ostrowski and Marsden. Hatton and Choset did some more work in the 2000s. But really, the original idea goes back to, I think it's Frank Wilczek, I forget, and another physicist back in the 80s. So it's a pretty old idea doing the symmetry reduction. But it basically says this: friction-dominated motion, and my initial slide said friction is a good thing. Friction-dominated motion, like slithering or swimming in low Reynolds number, has a linear shape-dependent structure called a connection, this A, that maps shape velocity, which is r dot in this equation, into body velocity, which is this expression here. This is just the velocity of the body with respect to itself. It's body velocity. And then there's another term which is related to the frozen body inertia and the momentum. But the important thing is this momentum is not the full dimensional momentum. This is a momentum that's just of the dimension of the space of frame motion. So it's a 6-dimensional momentum and something that depends on shape. This equation is much simpler than the sort of Hamiltonian dynamics we're used to, in the sense that we don't have a high-dimensional momentum. And in particular, this becomes simple if you can control shape, which is the situation in most cases in robotics. We have high-gain feedback on our actuators. If our actuators are strong enough to control the shape of the robot, and if we can measure the shape of the robot, really we've reduced the dynamics to 6 dimensions. If we got this connection object identified, if we can build this connection object relating the shape to the body velocity, the dynamics are just the momentum dynamics. And that leads us to the conclusion that there are really 5 different kinds of movement. The simplest kind of movement is what you get with a robot arm that's just in place. And that's holonomic movement all the way on the left. There's a direct relation between where the center of mass of the arm is and the shape and the values of all the joints. Unfortunately, robot arms can't move through space, so they're not important for locomotion. But if you just switch that a little, you connect a bunch of robot arms on a body and just let them plod along slowly without slipping, just attach them to the ground and then move relative to the ground. You can do piecewise holonomic motion, and that's a good way to move. In fact, when humans walk, this is what we do. We do piecewise holonomic motion. Our foot is planted on the ground. If I track down all the joint angles to my center of mass, I could tell you where my center of mass is by looking at the shape of my body. Now, one step beyond that is the Stokesian non-holonomic motion that appears in high viscosity systems or high friction systems, where we have the connection which is linear. And as you'll see,
when you speak about friction, you speak about viscous friction.
Well, so it actually works for
friction may be much more complicated.
So it actually works also for Coulomb friction, which is really surprising, and I won't have time to talk about why. But it does actually work for Coulomb friction. But it does work for Coulomb friction as well, and that was a huge surprise to us. In fact, we were not expecting it at all, but we've seen it empirically, and we now understand it theoretically as well. But we can also have a situation where there is a little bit of momentum and it decays quickly. The perturbed Stokes regime, which is something that my group analyzed and developed, and I'll talk a little bit about that. And then finally, all the way to the right is what happens when you have fully dynamic motion and you actually need a fully developed momentum equation. So just knowing R and R dot, you can't tell the body velocity. There are multiple solutions for different values of momentum. But what this means is going left to right, we really have more and more information that's needed to predict where we'll move to in space. Piecewise holonomic, we need to know where the last leg was planted. Stokesian non-holonomic, we need the body velocity, but there is no momentum. Perturbed Stokes, still sort of the same. You can mostly ignore momentum, and then dynamic, you fully need momentum. But these 2 kinds of movement are really pretty obscure. Not many people have studied them. And I think one of the things I hope to convince you is they're actually pretty important and pretty useful for learning locomotion in practice. Okay, so now I'm going to tell you, well, how do we use this theory? Okay, so I've given you 2 big ideas of dimensionality reduction and what they are.
Is this a point for questions?
Yeah, this is a good point for questions.
Any questions from home, from Zoom? You can unmute and shout your question.
Okay. I will continue blithely through these slides and not wait. You need to be Israeli and shout. A while ago, Ross Hatton actually did this experiment where they tried to estimate the connection. We know it exists theoretically. Let's just measure it empirically. They took this 3-segment snake, put it in a pool of beads, measured all possible combinations of joint angle and joint velocity, and computed empirically a connection. There's a problem with that. That's very, very inefficient when you have lots of joints. In fact, trying to get the exhaustive empirical approach suffers from the curse of dimensionality. As the dimension goes up, the number of samples you need grows exponentially, and life is really hard. But I had done a lot of work on phase reduction of animal motion, and we came up with the idea of combining the two approaches. Let's just build a connection model in the vicinity of a gate. So we have some cyclic behavior. We'll just build the model locally around the behavior we're actually observing. Oh, yeah.
For the sake of the guys who...
I'll try and do that. Let's see. There we go.
No mandatory. You can give
Restrict our attention to the vicinity of a gate. And the higher dimension we have, the more savings we have here, because we're basically sampling a one-dimensional piece of a higher dimensional space. And then if we have this local model of the physics, we can use it to make an iteration step and improve our gate with respect to some optimization criteria. And that way we can do an optimization. Why is this a good idea? Well, often we don't know the physics. And even if we did, the robots break and then our physics changes. And also gates are pretty high dimensional objects. So, this is already, it's already pretty hard to optimize them. So the approach is we get local models, we simulate the gate gradient against this local model. So even though the gate is a high dimensional object, so the gate parameter gradient requires a lot of experiments to compute. We don't compute it against the physical robot, which will break if we did that many experiments. We compute it against the local model which we built. And then we do a gradient improvement step. So how do we build this local model? Well, we start out with the idea that we split our shape into large scale changes along the cycle. That's the variable theta. This is a one-dimensional thing. So theta just is an image of a circle in a higher dimensional space. And a bunch of small perturbations off of this nominal motion, which although they're full dimension, they're small. And so we can do better modeling. So R is theta plus delta. We take this expression A of R times R dot, develop the R's into thetas plus deltas, do a simple Taylor expansion of A, because we're only caring about small deltas, so we can just model the dependency on small deltas with a Taylor expansion. Do a little bit of algebra, and we get basically a least squares problem. These regressors give us these coefficients. We can make a big table. Do this for each phase along the cycle, each little slice along the cycle, and we get a model of our physics. Okay, so this is a very, very simple way to learn physics. It's a local model of the physics, local to each portion of the cycle, and it's a first order expansion in each part. We parameterize the gates by just taking an ellipse and adding a little bunch of bumps on it. And that's the space with respect to which we're computing our gradient. So it's a pretty high dimensional representation. We could never do that many experiments on the actual robot. And now there's only one problem remaining, which is how big a step can we make every time we build one of these models? And so how good is our data really? And this is a problem that I often see people in machine learning don't pay as much attention to as maybe they should. So what we do is we take the covariance of the deltas that we have, the perturbations away from the cycle. This can be used to define what's called the Mahalanobis distance, which is basically the distance that is aligned with the covariance matrix. And so level sets of this represent surfaces of equal probability. And by evaluating how far we are in terms of the Mahalanobis distance, we can get a reasonable bound to say, are we in our data or are we outside our data? Are we extrapolating or are we interpolating with respect to the data we have? And so we make sure that we do not go out here where we don't have enough data to justify what we're doing. We have a single direction to explore, the direction we have by the gradient. And on that one direction, we do a line search and find our best solution. So that's the optimization algorithm. We build a local model, construct a gradient from it, get a bound on how far we're allowed to move along that gradient. And in that line segment in the high dimensional space, we find the best spot. Okay, what does this do? Well, here's a video. So we start out with a fairly long 9-segment swimmer. We let it swim for a while. It's a stochastic simulation, so there's some noise added to the system. Then we get a cycle, we compute the Mahalanobis distance, do a gradient step, we reproject this on the coordinates of the new motion, rinse and repeat. And as you'll see, pretty quickly, and by pretty quickly, I mean within about 9 iterations of the simulation, which will take, on the order of maybe 3-4 minutes on a laptop, this simulation will find what in this case is power optimal swimming gait on a space which is of dimension 264. Okay, so the space of gates over which we did this optimization is nearly 300 dimensions, but we could do this in 9 iterations because of the power of this approach. And so, of course, it's not enough to do this once. You need to do it a few times and convince yourself that this isn't nonsense. So we tried this with different levels of noise and did 60 iterations to make sure that we're convergent. Actually, after about 30 iterations, we pretty much reach the maximum. Here you see the covariance of the population of trials because we did many repetitions for 48 simulations in each of these ellipses. And all of the simulations at all the levels of noise reach approximately the same cost of transport. When the system's a lot noisier, it's a little bit less efficient. The optimal cost of transport is still not quite as good as systems that are less noisy. Okay, so it works for various levels of noise. What about various initial conditions? We started out our system with only 2 joints moving, and we changed which joints moved. So we tried all these different combinations of initial conditions, and we get the same result. So basically, this is a pretty robust optimization that gives very predictable outcomes. So the next thing to do is say, okay, what else can we do with this tool? Can it do other interesting things? Can we, for example, understand how animals swim using this? Well, we got some colleagues to give us some nematode swimming data. We then calibrated the parameters of a standard low Reynolds number swimming model, the Purcell swimmer, to the data that we got. So to convince you that we did a reasonable job, green is our swimming data, and blue is our simulated motion of the same nematode given the shape change. So we're going from shape change to motion in the world, and we're doing a pretty decent job of simulating how it swims over multiple cycles. So now that we believe our physics, we can ask, what is a nematode actually optimizing when it's swimming? Let's try and optimize for the most efficient swimming. Let's try and optimize for the fastest swimming. Which of these are nematodes doing? Well, it turns out they're doing neither. So blue is the fastest swimming, purple is the most energy efficient swimming, and green is what the nematodes are actually doing. So they're doing something in the middle. And that's sort of a fact of the practicing biologist, is that animals do what they please, and it's very rarely anything that's immediately obvious to us. But it's not enough to do things in simulation. We also need to see if it works on actual robots. So here is a 5-segment robot. It starts with that motion, moving one motor, which doesn't get it to move at all. It's a wheeled snake robot. And as you will see, this very same optimization we ran in simulation now gets this wheeled snake robot to figure out how to drive to the right in our arena. And by the time we reach trial 9, you'll see it does a pretty good job. And this is the optimization in real time. Okay, this is how long it takes to learn how to move with a robot. So compare that to other machine learning tools, and you'll realize this is a pretty powerful tool. 10 cycles is where we stop the optimization. So you see, it's a pretty good motion. Yeah, you were raising your hand in just the right time. Okay.
I have a question about the previous slide. You showed like the movement of the actual animal and 2 results of your optimization processes. And you said it's neither, but it seems like a combination of both. So I'm wondering, did you try maybe do like a Pareto optimization? Maybe it's like some point on the Pareto front between those two?
We didn't push this very far. You might have noticed there's no publication at the bottom. This was a conference talk and we never followed up on it further. But you know, I forgot to say, I'm desperately looking for students. If there's someone who wants to work on any of these problems, we have money from the Khan Foundation. I would love to work with you. There are a lot of unfinished projects here. But the things that are finished have a citation at the bottom. So we did, however, find a little problem in our data. We do linear regressions on non-centered data because there's an average velocity, right? Velocity is not on average 0. So we should expect that the average application of AK to theta dot equals the average AK applied to the actual theta dot. These equations should hold. They don't in practice. There's a freedom in our regression that allows these not to hold in practice. We were very, very puzzled by this because this is an internal consistency that should exist algebraically in our model if our theory was correct. And so the immediate suspect is that our physical assumptions are wrong and there's a little bit of momentum in there. And so we really asked, could this be due to some momentum, some residual momentum? And sadly, I don't have time to talk about this in detail, but my student, Matt Qualheim, figured out a way to analyze this and showed that, and this is the most terrifying slide I'll show this talk, it's all equations, that you can take this whole regression that adds perturbation terms related to the rate of decay of momentum. This epsilon you see in the equation is the rate of decay of momentum. And you end up with a regression that has basically the same terms we had before. I'm sorry, I should use a mouse for this. Regression that basically has the same terms we had before, except for one new regressor, which has a coefficient of magnitude epsilon. So basically, if you have momentum there, you get almost the same model in terms of data-driven modeling as you do when there's no momentum at all. And that might be why things worked out okay for us. And so we said, okay, well, what about adding this missing coefficient? Does that really help in intermediate Reynolds numbers where momentum exists but decays quickly? And the answer is yes. What you see here is a figure that shows as the x-axis here is the log 10 of epsilon. So we're going 6 orders of magnitude range of Reynolds numbers from really, really friction dominated to really, really inertia dominated. And you see that in the middle, we have this big increase in the accuracy of this model. So when there's too much inertia, the connection no longer is a good model and this doesn't work. When everything is really, really dominated by friction, you don't need the higher order terms that we're adding. But in the middle, they actually improve the model quite a bit. And I'll show this in simulation. So the simple connection is in blue, the perturbed Stokes extension is in green, and red is the full fluid dynamic simulation of the swimmer. And after a lot of cycles, green is still pretty much spot on red, blue has drifted away a little. So for intermediate Reynolds numbers, this improves. So okay, this is nice. Can we extend this paradigm even further? And so we decided to look at underactuated systems.
Any questions, maybe?
Again, I remind people, this is the time for questions if you have any.
Questions from Zoom.
So Shai, I'll ask a question. So gravity. So I know this connection does fail when you add gravity. What's the connection to that to the perturb? Is it possible to also add some kind of simple kinematic system climbing up a hill or gaining gravity, and will this still work there?
Well, I mean, what gravity does is it breaks the symmetry of the problem. So you have a reduced symmetry when you include gravity. That's what it changes.
Right.
As I'll show you a little bit near the end of this talk, for a bunch of real world systems, it seems this still works fine, even though gravity is definitely playing a role. And there's partially a pun because there's pitch and roll there, but you'll see that it works empirically. That's the best answer I can give you right now. But again, I'm happy to talk more about this in detail.
Okay.
But you are right that it breaks the symmetry and generates a problem using connection. So we started to think about what happens if you have an underactuated system. Why do we care about underactuated systems? Because most soft robots, and soft robots are a pretty popular field today, most soft robots can be modeled as a bunch of passive degrees of freedom actuated by some active degrees of freedom. So let's split our shape into controlled coordinates and passive coordinates. We can only dictate the controlled coordinates and the rest are passive. And similarly, the wrenches that are applied to these bodies split into active and passive. And it's been shown that under a broad range of friction conditions, there is a linear relationship between the torques and these are inertial forces between the torques and the velocities. And this is this mass matrix N. So we can split it as well and start writing our equation. So for Stokesian systems, theoretically, we have torques that depend on shape velocity, and the body velocity, G inverse G dot. But G inverse G dot itself comes from a connection. So it actually, the torques only depend on shape and shape velocity. We solve for the passive motions and we can pull out R dot. Basically, it turns out that the passive degrees of freedom are in a affine map, state-dependent affine map from the controlled degrees of freedom. That's pretty surprising, I think. And because the Stokesian motion itself is also affine, if the reaction forces in the body, the friction forces in the body are themselves affine, everything here is affine. And it turns out the reaction forces being affine in the body mathematically sounds complicated. In terms of physics, just means we only have regular dampers. We don't have nonlinear damping in the body. That's all we need. So the body has linear damping as the dominant way it reacts to velocity. Basically, everything falls out, and we still have something that looks very much like a connection, except it's affine instead of linear. It has an offset velocity V0 and not just a connection-like term. This A is not the A we had before. It's a different A. It has a whole bunch of new terms hiding in it, but it's still a linear term that's non-linearly dependent on R and linearly dependent on the controlled shape variables. And the passive shape variables are also an affine map. So this is a really, really simple model. The physics is basically telling us we can get a really simple model of these systems, even though we thought of them as nonlinear because of all these passive degrees of freedom that interact with each other. What is it that made these systems suddenly appear like they're linear when they were nonlinear before? Is the fact that we are observing RP. So casting that into the language of machine learning people, what I would say is the passive degrees of freedom are a bunch of features that linearize the representation of the system. So with respect to the passive degrees of freedom, if we can observe them accurately, the dynamics become affine, and they're a lot simpler. And so we tried a bunch of different models. I think most impressive among these is the model at the bottom of this. It's a 9-link per cell swimmer. It has 2 actuators. All the other actuators are passive. We get 87% of the variability of those motions predictable from our models. Our model is pretty good. It's almost 90% of the motion is predicted by a model that's affine, even though most of the degrees of freedom here are passive, and there's this long chain of passive links that we're driving just from the end. So this works for underactuated systems as well. This got us ambitious. So if it's so easy to learn a single motion, maybe there's an advantage in learning multiple motions. And here's why. If you're a roboticist, one of the things you learn, in your cradle as a roboticist is to solve navigation problems. We want to move through space. We want our robot to be able to go somewhere. But the way we do that is we solve a planning problem. And often when you have legged robots or robots that have some sort of periodic motion to propel them, you compose that motion from pieces. Walking forward and turning sideways, for example, is a pretty popular choice. But that's actually over-constraining the optimization. Why should I pick walking forward as one of the two pieces I use for my robot and turning sideways as the other? Maybe there's a walk forward and turn motion and another walk forward and turn motion that are much more natural for the mechanics of my robot. Let's not over-constrain our optimization. And so what do we really care about? What we really care about is accessing all of space. That is, thinking of SC2, if the space of rigid body motions in the plane, can we quickly span a piece of SC2? And so because we can optimize single gates so easily, we decide to be ambitious and optimize a library of gates together to access a large piece of SC2. Formally, the way we do that is imagine that each motion we have generates one rigid body motion. So MA is, say, one motion, MB is another motion. We can compose them in any combination, so we can generate words out of these motions. And we can look at the horizon of, say, 3 cycles into the future. What can we compose out of these motions? And ask ourselves, how well does this span the space of rigid body motion? So how do we metrize this? We associate weights with our goal locations, these W's. We have goal motions we'd like to span. These are our G's. And we're taking the minimum motion, the minimum distance motion. So the distance here is the distance on the log of the matrix, on the log of the group. The reason, the rationale behind this is if I pick, say I went here, I went red 1 step, green 2nd step, blue 3rd step, I got to this point. Nearest point is this gray point. This distance is very short. On a short distance on the space of rigid body motions, we can take the logarithm and get a good measure of distance. There's a little bit of choice there. How do we measure rotational distance versus linear distance? I won't get into the details of that. Just say, this is how we represent our goal function in terms of covering the space of rigid body motions. And then we tried this with swimmers that have various numbers of joints. So 3-segment swimmers with 2 joints all the way to 8 joints. We optimize them for coverage, and then we break them. We lock some of the joints. So now they need to move, but the robot is damaged. And we restart our learning from the state we have when they were broken. And as you see in terms of convergence here, they recover very, very quickly. This 3-joint robot has a little bit of trouble because it went down to 2 joints, which is the minimum needed for motion. But basically what happens here is the more joints, the faster the system learns, which is sort of the opposite from what usually happens in learning algorithms. So usually when we make the robot more complicated, it's harder to learn. What's happening here is sort of the opposite. The larger robots actually learn more quickly and recover from damage more quickly, which is sort of what we're used to in organisms. Let me show you an animation of this. So we have our swimmer. It starts with a pretty useless set of gates, changes them, does a few iterations, and gets a pretty good coverage of this space of motions. And now we break a joint, and it again loses some of that coverage, re-optimizes, and after the new optimization, it can again access most of the space, okay? So we have a paradigm here where the ability of this robot to navigate through space is recovered very quickly despite damage. It can learn how to move in a new way after it was damaged. And I'm going to speed up a little because I think we're getting close to time, and just say what you see here is pre and post injury as a function of number of joints on the left, and you see that for a large number of joints, there's basically no loss of performance after injury, which is sort of what you'd hope. To show that this works for actual robots, we did this sort of learning algorithm on a robot made out of sticks. So we just grabbed some sticks from the backyard, attached them, did the learning algorithm. And again, this works for a legged robot as well. So in 20 minutes, we basically learned a library of maneuvers for this robot.
Shai, is right now mostly you showed going forward, so the cost function, you just added that as going forward, turning and things like that. You can as easily do as well if you add a different goal.
I'm not doing a separate going forward motion and a turning motion.
Right. So in this case, it's a rich library of motions altogether.
Yeah, and this is just one of the motions in that library.
Okay.
Okay, I should have clarified that. Yeah, that's it. That's a good question. Okay, so the question is this really a new way to model motions? And I'll take the last few minutes of my talk to convince you that this is a pretty good way to model motions over a broad range of systems. So we have this next thing, we have piecewise holonomic systems, which are a special case of Stokesian motion, which have a linear connection, which are a special case of the perturbed Stokesian motion, where the dependency on velocity is slightly nonlinear, but we still don't need momentum. And so this is the space of motions we're looking at. And we looked at the following systems. We looked at ants. I won't talk about cockroaches, but we looked at cockroaches as well, and two robots that I have in my lab. And the reason we looked at these is because what we care about is slipping. So piecewise holonomic motion is what you get when you have little to no slipping, which is what the ants do. But if you look at this robot here, I should mention that the colored areas are legs that are on the ground. These are traces of the feet on the ground, and the colored areas, the larger they are, the more slipping was going on, the more that foot was moving while it was on the ground. So you see there's a lot of slipping in the robot on the bottom right, very little slipping in the ants. Glenna and Nick did wonderful work on ant motion tracking, and so this is joint work with them. They have a machine vision-based ant tracker, and so we had literally millions of cycles of ant motion, which we could do analysis on. And so we partitioned them into 12 categories. When the ants are going really slowly, which is that innermost sector in that pie chart, we don't use that data because they do all sorts of different behaviors when they're really slow. But 25th percentile all the way to maximal speed, we split into 3 parts. And we also split the data into going right and going left. The data you see here is just going forward, and we're comparing the shape of leg motions, going slowly and going quickly. And you see that basically the legs go through the same motions at all speeds. So the ants are behaving like a kinematic system. Even though they're going much faster when they're going fast than when they're going slow, all they're doing is exactly the same shape, faster. By the way, not uniformly faster, but I'm not going to show you that graph here. But so we can ask, can we take the training data from the ants going in the orange spot, so it's middle speed, not going right, left, build our model there and predict. And we tried 3 different kinds of models. The simplest model is just take the average motion in the middle and use it as a prediction for the other motions. That's a baseline. The dark gray is, let's just rescale speed. Let's rescale the average speed of the ant's motion to match the new category of motions. And blue is our data-driven connection model. And you see that the data-driven connection model and the scale speed kind of form the same way. And this is on moving forward. And they're not doing great, honestly. They're only predicting about a quarter of the variability. But now we go to a behavior that's completely different from the behavior we used in the training data. We look at turning motion. So we try and predict how much is the ant going to turn using data collected when the ants were going forward and intermediate speed. Using a non-turning data to describe turning data is just useless. You see the prediction is basically 0. But the data-driven connection model can actually tell us that if the ants change their body shape in the way they change when they turn, they will in fact turn. That is, it captured the physics pretty well for all these other domains. So we trained it only on the center block, but it predicts the whole data set pretty well. So that worked pretty well with ants. Let's look at our robot. I'll just show you a little bit so you see how much this robot slips. It slips a lot as it turns. We look at the foot motions and the body frame. The foot motions are consistent, so the robot is basically doing a geometric motion. we give it different levels of turning commands, and those are the three collections of turning commands, three bundles of lines that you see here, but we also go at different speeds, and you see that what governs where the robot ends up is the turning command and not the speed. So there isn't a lot of inertial effect in what's causing the robot to turn. In fact, with different steering parameters, if we look at how much turning has happened per cycle, it's not dependent on the speed at all. Okay, so what we're seeing here is exactly what we'd expect out of a connection model, the speed independence. It's a geometric phenomenon rather than a dynamic phenomenon. And indeed, if we look at how well the data-driven connection predicts these data, it does a really good job, both in predicting forward velocity and rotation velocity of the robot. I'll just show one more small thing, and that is our collection of multipod robots. They have a variety of different numbers of legs, and we've tried them in a variety of different gaits. It turns out that everything you saw there, all these different robots doing all these different gaits, fall on the master curve you see on the left, with very, very little change dependent on frequency or leg number. So even though these robots have different numbers of legs, there's so much similarity that one master curve governs how they interact with the environment, and that master curve looks like it's geometric. So what I hope this last batch of results convinces you is that those two understudied domains of motion that I talked about are actually really relevant for modeling a whole range of robots and animals. This is actually working pretty well, which, because the robots are definitely governed by Coulomb friction, was a huge surprise to us, because this should only work for viscous friction algebraically. And why it works for Coulomb friction is pretty surprising. So this is basically my conclusion. Stokesian connection models are really easy to learn from the data, and they apply to most kind of friction-dominated motion, not just nematodes swimming in a viscous fluid, but also multi-legged walking when there's a lot of friction in animals and in robots. And so this is actually a lot more common than you think. These friction-dominated models are actually a lot more universal than you may have thought, and they're a lot easier to learn. Thank you.
Time for questions in Zoom first.
I have a question from Zoom.
Yes, go ahead, please.
I was curious about in the portion of the talk focused on coverage in a lead group or in SE3 or SE2. I was wondering how the optimal generators might depend on. I'm assuming that you are fixing some epsilon, the radius of a ball, and you want to cover SE2 or SE3 with, say, epsilon balls. And I was wondering how the optimal generators depend on epsilon, if you have any idea about that.
Well, so thanks for the question, Matt. And I think you're leaping to a conclusion here, which is that the distribution that we're trying to model is a uniform distribution on the group. But that's actually not what we're doing, because one thing we realized is that different types of planning problems might require different types of maneuver libraries. So for example, if I want to be able to go at a variety of different speeds, but I don't expect to need to do a lot of sharp turns, I might want a lot of data points, a lot of rigid body targets in the direction of motion and very few to the side. So I might want a very non-uniform density. So I think that's for starters. I think a more interesting question, which we don't have a good answer to, is this is a very discrete way to do this. I would love to have a measure theoretic way of doing this. We scratched our heads a lot. We're not good at measure theory help. So I'm sure there's a better way to write this, but this is as far as we've managed to take it so far.
Okay, thanks.
Hi, Shai. This is Miriam. How are you doing?
Hi, Miriam.
Okay, first of all, nice to see you and great talk. Very, very interesting. I'm curious about the portion of the talk that has to do with learning, where you had a local model and then used the gradient to determine how to change the parameters. So if you can elaborate more, like the gradient was computed with respect like in reinforcement learning, you had like a different reinforcement that you gave if it was more energy efficient or if it was faster. I mean, so it was like a reinforcement learning type of gradient or?
Yeah, so let me try and explain that a bit better. So the first thing we do is we build a local model of the gate. Okay, so this is a very fast to evaluate, basically numerical object, where we could give any possible motion that's within a tube around the behavior that we saw before. And we would get a pretty good guess at what the physical outcome would be. So you can think of it as just a very fast simulator. And it's a simulator that was tuned just to the data of the last experiment we did. And now with the simulator, we can now compute the gradient of the various parameters that are used to define the gate. So say in that example I gave before, there were 284 parameters defining the gate of that 9-segment swimmer. We could do that gradient of whichever goal function we wanted, which in that case was cost of transport, it was just the energy spent, and then do an iterative step. So it is really just a numerical gradient computation computed against a very, very fast simulation. And the only reason that simulation is valid is because we learned it from an experiment that actually had data in the entire domain where we built that simulated model. Does that help?
Okay, let's consider, for example, the energy efficiency. So, but the energy efficiency you compute for this motion, for the different, let's say, cycles in this motion, and then you compute the gradient, or you use the model to predict the energy efficiency. I guess that's what I'm confused.
So we take our gate, and it's 300 dimensions. We perturb in each dimension and run our model. It's very fast. So we literally do a numerical gradient. Just
okay, I see. Okay. So you actually perturb in each dimension, in each direction. You don't do like. Okay, I see what you're saying.
Yeah, the reason this is an
okay.
The reason it's an advancement is because this model is so fast and so simple to create.
Okay.
Because if you tried to do that many experiments on the physical robot, it would break 10 times.
I see what you're saying. Okay, got you.
More questions? Questions from the class? From Zoom?
That's it.
Okay, thank you very much. Let's thank the speaker again. It's complicated days. Hope everybody will feel well and will get over the Omicron until the next one. Okay, תודה רבה.
Thank you.
תודה שי, תודה יזהר.
רועי, ביי, להתראות.
תודה להתראות.